My name is Lorenzo Gallo and I am a second year PhD in Material Science at CNR IMEM Institute in collaboration with the Physics Department of the University of Parma. The topic of my PhD and the title of my talk today is Magnetic Shape Memory Heusler Compounds for Low-Grade Heat Harvesting. In fact, today I will talk about how I and my group have synthesized and studied some nickel-manganese-based Heuslers compounds to be used for the thermomagnetic energy conversion of low-grade heat application, and how we tested them directly in application condition with the device developed by us. But let's start with the problem, and the problem means energy conversion. In fact, it is the basis of our modern society and plays a fundamental role in everyday life. However, the conversion process from primary energy carriers to energy service is always characterized by large losses. In fact, in a simulation of the 2016 shows that an amount of 155,000 petajoule was emitted into the atmosphere in the form of heat at a temperature below 100 Celsius degrees. That is the so-called low-grade heat. To be clear, this amount of energy in 2019 could have supplied the United States, the whole European Union and China, and something would be left to supply the whole Australia. So it is clear that the idea of recycling even a part of this very huge amount of energy is very attractive from a scientific point of view. Unfortunately, it is possible to use magnetic materials that, exploiting the thermomagnetic cycle, can convert low-grade heat into useful energy. But what is a thermomagnetic cycle? Well, it is a particular thermodynamical cycle composed by two isothermal and two isofield transformation. On the left of the slide is shown a scheme of the cycle. And without going into the details of the cycle, we are only interested to know that for energy harvesting application of low-grade heat, usually the hot source has a temperature below 100 Celsius degrees, while the cold one temperature should be the room temperature. And the fact that in the end of the cycle, the system can convert heat into an amount of useful energy that is proportional to the difference in magnetization of the magnetic material used at the temperature of the two sources. On the right of the slide you can see the operating scheme of the thermomagnetic device that we developed to test different materials. But which kind of material we are looking for? Well, in general, thermomagnetic materials should present a magnetic transition near room temperature, and in the case of the first order transition, its thermal hysteresis should be as low as possible. Of course, they also should be possibly free of critical elements and cost effective. But finally, they should also have a high thermal diffusivity to exchange heat quickly and to increase the speed of the cycle. On the right of the slide you can see that the scientific community is evaluating a large number of families of material for this kind of application. And in my work I'm focusing on Heuslers compounds. Heuslers compounds in fact are a very large material family with the general formula X2YZ, where the first two elements generally belong to the D group, while the Z elements belong to the P group. One of their most interesting features is the fact that some compounds exhibit both a second-order Curie transition and a first-order magnetostructural transition, the well-known martensitic transition, that is characterized by a very high and sharp difference in magnetization. Furthermore, Heuslers generally exhibit good thermal properties, and they are also radar-free. But probably the property that makes the Heuslers very promising for this kind of application is the wide tunability of the critical temperatures of these alloys. In fact, it's possible to shift the magnetic transition temperature by slightly change the composition of the compound. Unfortunately, many Heuslers exhibit a large thermal hysteresis across their first order transition, and this is the reason why the characterization and the test of thermomagnetic properties of our sample that we are conducted for the moment are only across the second order Curie transition. So Firstly, we synthesize a set of nickel-manganese steam samples by varying the ratio between nickel and manganese, and we conducted some magnetic measurements. For example, in the left of the first figure are shown some susceptibility measures over temperature conducted with a TMA, thermomagnetic analysis, that is basically a susceptometer with an applied field of 1 millitesla. While on the right of the same figure are reported some isofield curves measured with an extraction magnetometer with an applied field of 1 Tesla. Then on the right of the slide are reported the Curie temperatures extracted from the TMA measurement and the values of the magnetic moment at 300 Kelvin. The reason why we decided to report them to this particular temperature is because we think that given the application of the energy harvesting of low-grade heat, their values at room temperature becomes particularly relevant. To summarize the results, we can observe the wide tunability of this set of samples of the Curie temperature that covers the temperature range between 300 Kelvin to 330 Kelvin. And this is, in our opinion, one of the reasons why we think that Heuslers compounds are very promising candidates for energy harvesting application. And let's move directly to the test of one of our material. The composition we choose is nickel 48, manganese 36, tin 16. That probably means nothing for you, but you have to know that this kind of composition presents a second order Curie transition exactly at 50 Celsius degrees. And firstly, we reduced the material, the compounds in powder, and we did a composite based on epoxy resin and graphene. We add some graphene to increase the thermal properties of the composite. The rotor has a diameter of 20 millimeters and a thickness of 1 millimeters. Actually, the device is being optimized just in these days. However, even before the optimization, the system could reach angular speeds of more than 50 radians per second, and with a hot source of only 60 Celsius degrees, and with a cold source temperature measured near the rotor of only 35 Celsius degrees. And in summary, the investigation of the tunability of nickel-manganese tin Heuslers compounds has been shown, as well as the development of a thermomagnetic device for the energy harvesting of low-grade heat to be used as a tester for different thermomagnetic material. In the very next future, we are going to test the thermomagnetic properties of new Heuslers compounds, but one day we'd like to test some old Heuslers exploiting their martensitic magnetostructural transition. But more generally, obviously, since this device is thought to be a tester for the magnetic materials, the more materials family tested, obviously the better. And thank you for your kind attention.